Okay, welcome. Adrian and I are from the SBB, as you heard. We work at the Platform for Research and Innovation, and we would like to present what we believe is the future of dispatching in railway system, and especially in the Swiss railway system. We can connect nicely to the first talk because we are also talking about schedules and punctuality, but we don't want to predict how punctual we are. We want to make us more punctual. So we look at this dispatching problem. The dispatching problem is Swiss trains, they run on a timetable. From time to time, there is small disturbances in the system, like in any dynamical system. For one side, we will have, for example, large passenger groups needing to board a train, takes longer than single people boarding, or you have infrastructure failures, or you have failures on the locomotive. So anytime you get these disturbances, you get delays in your system, and you want to keep these delays as small as possible, and you don't want them to propagate along your system. So we need to interact. Interacting means dispatching. Today, this is done by a lot of human effort with the help of a so-called rail control system, so by computers. They help restabilizing the system to get as close as possible to the timetable that we had. And as you saw in the previous talk, we're quite good at doing this. So what can we actually take? What are the actions that a dispatcher does? And we're just showing you the two basic binary dispatching actions here that you need to organize train traffic on tracks. First of all, trains, in contrast to cars, cannot just simply pass each other along the tracks. So it's very important in what order trains run. So if one train is delayed, it's very important to not get other trains stuck behind that train. So at any switch, we can decide on what order we want the trains to pass this switch by setting the signals. So in this case, we, for example, would let the passenger train pass in front of the freight train. And this might make sense due to the different speeds of the train. Also, delayed trains, you might let them go behind other trains. Now, if you come towards a switch from the other direction, there's another choice you can make. You can reroute the trains, so we can decide to either just let this train go straight or reroute it. This is needed if you want to pass, so one train has to go to the side so the other train can pass. Then, of course, also we have more than 800 destinations in Switzerland that we want to reach, so we need to be able to reroute the trains to reach all the destinations. So the dispatcher, simply said, doesn't do anything else than taking these two different binary decisions. So any train run, we take, for example, this train run on this small topology, can be illustrated or depicted as a path in a binary tree. So you take a decision of rerouting, for example, at the first switch, then you decide to go straight. Then there might be other trains, so you have to decide which ordering of the trains I want. Again, you go on and on and on for any train run. Now, to get the train to run on time through that system going by itself, it's very simple. I mean, that's not hard at all. But now the problem comes between the interaction of trains. So we have trains running at different speeds, and we have a lot of trains interacting. So if you look at the complexity, if we have one train on this simple topology that you saw, there's 30 possibilities. Now we have many data scientists here, so what's your guess if we have two trains of this network? Do you think we stay in the few hundreds or in the few thousands of possibilities? Please raise the hand if you think it's a few hundred. A few thousand? Okay, a few had it right, the few hundreds. The others should maybe go back and do some more math. But let's try it again for 4 trains. What do you think happens if we have 4 trains? Do we now go up in the few thousands? Please raise your hand. Or do we even get up in the few millions? Please raise your hand. Or even higher? Raise your hand. So for this simple topology with 4 trains, we have approximately 8 million different possibilities of dispatching these trains through the system. So approximately the population of Switzerland for just 4 trains. Now, if you have 80 trains, it starts exploding. So that's already more possibilities of dispatching than there is atoms in the observed universe. Now, 80 trains sounds like a lot, but the SBB has more than 10,000 to 15,000 train runs every day, And our topology looks a bit more complicated than what we depicted here. So it's an unimaginable number of possibilities of dispatching every day. Now, if you look at the binary tree of the whole of Switzerland and dispatching, and you wonder, well, what decisions lead to a good day? That's a very hard thing to know. Some paths will lead to good days, and some paths will lead to bad days, where bad days are days where you have a lot of delays in your system. Now, you saw before, somehow we're able to do it because most days are green. Most days work quite fine. And one reason is that we have constructed our schedule in that way that we have temporal buffers that allow us for small deviation and we can still solve the problem. And the other part is we have a lot of people who work hard to keep trains on time whenever delays happen. Now, predictions for the future of the mobility needs of humans all over the world, but also especially in the urban areas in Switzerland, predict we will get 30 to 40% more traffic on the railway network. So this task will grow much harder. And this is where our work focuses. Here, we want to come up with a new system that will solve this task more efficiently in the future. So today, this is the situation we have. We have the Swiss railway network, and we have dispatchers who interact with that system to try to keep it stable. And we have a lot of measurements, as we also present in open data, but internally we also have a track record of what was happening in the past days. Now, the idea was to go back and just learn from the data we have to improve our behavior for the future. But there's two big flaws with this approach. First flaw is the interaction. A dispatcher is mainly working on his intuition and his experience. Now, if we go back and look at the data and we tell him, well, let's be creative tomorrow, just try something new, he will never do that, and you as passengers would be very unhappy, because we cannot know what will happen to a dynamical system if we just freely experiment. So we are bound to do similar things. This is the same with the schedule. We can only do minor improvements every year because it's hard to imagine what happens if you change drastically. The other part is the data that we collect. Even though it's millions of data points, the information contained is quite low. Every day you see one realization of train traffic of that day. You don't see what alternatives could have happened and improve the system. So this is where we came up with the idea to extend beyond reality, and we started to create a high-performance simulation of the Swiss railway network. On this Swiss simulation of the rail network, we can again make observations as we can make in real life. Now, we can learn from these observations we make, and we interact. So this is the loop as before. But now we have two big improvements. Here, we can freely experiment. Nobody cares if trains are delayed in a simulator. So here, the dispatcher can try whatever he likes and see if it improves the system or not. Furthermore, when we validate our artificially generated data against the historical data, we don't have the problem of limited information anymore. We can generate a lot of different variations of every day and see what improves. Now, the bottom loop can be done by humans, so we can interact with the simulator and learn from this. But this is highly inefficient. So we go here with the approach of machine learning and using recent improvement and successes of reinforcement learning and the setting of our problem, we chose to go with this approach. Just as an overview, reinforcement learning is very well suited if you have an environment where the dynamics are known or given to you, but you don't know what optimal strategy you have to use to survive or to get the best result in that environment. So that environment is very famously known for games, the Atari games played, or AlphaGo, for example. Then you have an agent. In our case, we use a neural network as an agent, and this agent can interact with this environment. You have an interaction with the environment. Your interaction changes the dynamics, so the environment evolves, and you give the observation back to the agent, so the agent sees what happens if it interacts. And then you give a reward back, and the goal of the agent is to maximize the future expected reward. So it tries to play or to behave in such a manner that the reward is largest at the end. For us, we replace this arbitrary environment just by our high-performance simulation, and we come up with our own reward function that rewards the agent for good behavior. Now, as I said before, we don't really know what good dispatching is, so we cannot reward the agent for every dispatching decision it makes. But rather, from time to time, we can reward the agent by saying how much delay we have in the system. And so the agent learns to dispatch based on this. To become a good dispatcher, you can imagine yourself if you would sit down in a dispatching office of the SBB and you'd have to route trains. You've never done it before, it's quite hard. And the same happens for the machine learning agent. So it needs to train for a long time. In the beginning, the interaction, it will probably be quite the poor dispatcher and do terrible things. But over time, it will evolve. And at a certain time, it will reach human performance. So the dispatching strategies should be the same as the dispatching strategies of the humans, or at least the performance should be the same. Now, humans, unfortunately, they die after a certain time, so they cannot improve anymore. And this is where machines have a big benefit, because they can just keep on training. So our target is to reach superhuman performance by letting the dispatcher agent train for 65 million years. So we want to generate a dispatching agent that has been dispatching since the dinosaurs went extinct. And by that way, it will get superhuman. I will now hand over to Adrian, my colleague, who will tell you how we managed to do this.
Thank you, Eric. Now you got the insight into our conceptual work and what we like to solve. And I like to dive a little bit more into the technical part. So you can imagine we cannot wait 65 million years in order to get our system trained. So what we did, Eric mentioned, we have implemented the high-performance simulation of the whole railway network. And this is really important. We need a really, really fast simulation before we can start learning. So we have the high-performance simulation. As the software module is based on GPU computing, so that means we can do it in parallel manner on GPUs. This is written with NVIDIA CUDA and C++. We have as well integrated the simulation software into our geographic and information system. We can use this software for dispatcher training, and of course we are using this system internally to learn more about railway system. So it's important for us, for Eric, and especially for me and for the whole group, to better understand what's going on the railway network. We have also done R integration, so we can writing R scripts and we can work with the software library as a package. And we have more than 1,000 test cases written there, including functional tests, regressional tests, and of course performance tests is really important to have a system, a stable system for training. And as most of the audience here are data scientists, you know very well the Python library. We have decided to switch from R to Python because there are so many nice packages we can freely use. The integration is done with C types and PyCUDA. May you know PyCUDA? PyCUDA is an excellent library if you need writing in Python scripts, CUDA kernel functions, so we can extend easily through Python our simulation software. We can prototype, and so we don't need write directly C++ code. And for the machine learning part, the reinforcement learning part, we are using PyTorch, Keras, and TensorFlow backend. One thing is really nice to see, if you have a high-performance simulation based on GPU technology, you can use it on any personal computers as well, on high-performance computers or big systems like the DX1 system, but it works also on personal computers and mobile computers. They need, or the machine needs just a GPU from NVIDIA. This is more or less how we have implemented the system, and this, you can think this is easy to do, but it's hard work behind. So just having a system like this, then you can starting with reinforcement training, because now we have an environment. You can see the complexity in our system. It's a really complex system behind. Even here is a full day animation of a full day simulation we do for the whole Swiss railway network, including all railways companies and infrastructure. So you see each point here is representing a train, and we do a full simulation of this train. So we do 1 second simulation step. That means we have to simulate more than 86,000 steps for 1 full day for 24 hours. Okay, we have done this full day simulation, 1 day, 24-hour simulation of all trains. We have more than 50,000 trains to simulate. We have around 31,000 signals, 13,000 switches, and around 800 stations to simulate. These numbers are impressive, I think. And we can do that on a Volta GPU within 17 seconds. This is pretty fast. And if we do only the physical part, that includes collision detection, and so we cannot collide with the trains, and it also includes the physical dynamic. We need less than a half second. If we include a little bit more railway specific stuff, means business rules, and including overfilling, so means we can detect deadlocks. That means we cannot face 2 trains on the track because they cannot cross. So we include this method. We need additional 3 seconds, and the total part is 17 seconds, but including 14 seconds only for the interactive part for the reinforcement learning. This is the most expensive part. We including in these 14 seconds, we need the state generation, so each agent needs his state set where it can take decisions and actions on the railway network. Here you see as a small part of our simulation. You see 4 trains. Each train is connected to 1 agent, so we have a multi-agent system. Finally, we have to do multi-agent reinforcement learning. It's more complicated than still reinforcement learning with 1 agent. Each agent here sees the local prediction of the future traffic, and they also communicate in a global manner together, and so we try to overcome the problem of dispatching. So if we have 65 million years to simulate to get the experience, and 17 seconds is 1 full day, so we have to wait 12,000 years. I think it's not feasible to wait 12,000 years to get the system trained. To overcome this problem, we decided to go another way. So we have the whole rail network split into sub-regions. The reason is on the GPU memory we cannot hold many different whole railway network, and if we split them into sub-regions we can do more parallel simulations at once. This is one reason, this is the technical part. The most important part is not that one. So the second part is if we do on sub-regions, we lose the dependence of the whole topology. So we try to learn on sub-regions and to scale on the whole topology, so we win the performance, but we can avoid that the system learns how the whole topology looks like, and so if we change once in the future, the system, the real physical system, the infrastructure element, we can overcome this problem. And each sub-region has the multi-agent reinforcement learning attached, and we do weight sharing between them from time to time during learning. So the benefit of this system is we can do that in parallel, and that means we can learn on sub-regions more efficient, more fast. It's really performant. And on the other hand, we can reduce the risk to overtrain on one certain topology. And how it looks like this parallel simulation, so that's just an animation of our simulation where you see not each scene is the same, so we do the training really in parallel. It's really tough to visualize, but this gives an impressive view what we are doing in our lab. So I give back to Eric. He says some words about our team who is working on this system.
Thank you very much, Adrian. And I'd like to close by giving you an overview of our team. So in this lab, we're 5 people working permanently and that the number of people is always changing. And for a project like this with interdisciplinary aspects, we think it's very important that you get specialists from every part. So we are mathematicians, physicists, neuroscientists, machine learning, software engineers, and we are a very diverse team. And together we believe we can propagate ideas like this much more efficiently. To take home, I'd like to share some of our learnings that we had, and especially when you work in a company like SBB that is very safety-driven, that is not allowed to fail, it can be quite hard to improve quickly and generate learnings. In these systems like this, we believe moving into the digital world, so making copies of either your system or abstractions of your system, can help fasten the learning loop. In this loop you can fail, so you see in this loop, every time you fail you can learn something from your failure and you can improve your system. And if you do this on the digital side, you can do this in a quick manner and in a cheap manner, and then you can bring your learnings back to reality to improve your real system. This is all. Thanks for your time, and we're happy to take questions.